So the next topic that we are going to be discussing is state uncertainty or partial observability. So till now we looked at deterministic actions and how to do planning, and then we looked at stochastic and non-deterministic actions. Actually, we didn't really look at non-deterministic, we went directly to stochastic actions. And then for partial observability, actually we'll split our discussion into handling non-deterministic uncertainty and stochastic uncertainty. The difference, I mean, say bad naming, but non-deterministic only means it's not deterministic, and it doesn't, for example, mean that you have distribution information. Okay, so you think basically that you might be in state S1 or S2, etc., Sk. You don't quite know anything more than that fact. You could be just in one of these states. Okay, stochastic basically would say this is 0.1, this is 0.3, this is, let's say, whatever, 0.7, and so adds up to 1. So there's a distribution over the states. Okay, for the action uncertainty, action outcome uncertainty, we looked at stochastic uncertainty directly. Here we will first look at non-deterministic and then go into stochastic for reasons that will become clear. In fact, there are interesting problems that can be handled without actually knowing anything about the distribution. And then when we get to the distribution, we'll look at POMDP models. Okay. Yes, sir.
Do we view states as a black box here?
So, once again, the issue is that you can always start with atomic and move your way up. Okay, so first we'll start with atomic model. Understand, I mean, if you don't understand any problem at the atomic model, you have no hope of understanding it any other level. Okay, so you should understand it at the atomic level and then talk about factoring and then also efficiency. Okay, so for the non-deterministic case, we will start today with atomic model, which is actually reasonably fast to get through, and then we will talk about factored models for that case. Okay, and then we'll actually talk about, next class we'll talk about how to generalize the planning graph style heuristics, for example, to support planning with these factored models in the case of non-deterministic state uncertainty. Okay, and then we will hopefully by next week we'll start talking about supporting stochastic uncertainty, and then there mostly I will spend time talking about POMDPs, which is just an atomic model for stochastic uncertainty. Okay, there isn't that much work on factor. I mean, there is some on the factored POMDPs, but I'll probably not get to it. Okay, so it's kind of important to understand this lay of the land. I mean, there is an atomic versus factored. There is also non-deterministic versus stochastic. Okay. And one of the things is that the problems are much more interesting in the stochastic case, in terms of the complexity of the problem. We'll keep seeing that as we go forward. Okay, okay, so where did this come? Okay, so this is a busy slide, but this is pretty much everything that you need to know about the atomic model for state uncertainty. Okay, first of all, when we talked about action uncertainty, we still assumed no state uncertainty. We assumed state is, you can actually see the state right away, whenever you want. Okay, but now that we came here, after having talked about action uncertainty, we can choose to have either deterministic or non-deterministic actions. Okay, so the assumption is that we'll spend more time talking about the state uncertainty aspect, but in terms of dealing with the state uncertainty, if you also have uncertain actions, it becomes much harder. If you have deterministic actions, it becomes easier, somewhat easier. Okay, and so in fact, okay. The main thing that changes in this is that the search up until now, search was always for atomic model, the search was always in the space of states. Okay, so you could have had basically you could have had a star search in the space of states when you have deterministic actions. Okay, and we didn't talk about this, but we directly went to MDPs. But if you have non-deterministic actions, then you can have AO star search in the space of states. Okay, AO star is and or search in the space of states. Okay, now what changes is, in fact, your state representation changes. You know, the agent doesn't know which state it is in. That's the point about when you don't know, when you can't see, when you can't sense your state, then you essentially don't know which state you are in. Okay, so suppose the underlying system has states S1 to Sn, and these are black box states at this point, right? Then basically the agent assumes at any point that it will only know that it's in some subset S of this set of states. Okay, full uncertainty means that you think you are in one of these n states. Okay, and anything you can do to reduce your uncertainty in state uncertainty is basically to make it small. Okay, so one other interesting question actually when we come into this is, I mean, after all, we're going to be eventually thinking about there being some goal and you're trying to reach some goal, right? Normally, in the past, we would be talking about progress of an agent in terms of becoming closer and closer to the goal. But now there is also this issue that the agent may not even know which state it is in. So there are essentially kind of two kinds of progress that an agent can make. One is reduce the state uncertainty. The other is get closer to the goal. Okay, and a complex combination of both would be useful in actually trying to reach the goal. Yes, sir.
If you don't know in which state you're in, then how can you measure distance from the goal?
If you don't, well, basically we will talk about this in the heuristics part. But in essence, if I happen to know that I can be in states S1, S2 or S3 and my goal state, remember one of the crazy things is goals were always sets of states. Right? It's just that when goals are sets of states, that's considered a feature, not a bug. Whereas when the initial state becomes sets of states, that's considered a bug, not a feature, right? Because you don't even know where you are. Okay, so in fact we'll spend a lot of time talking about heuristics in this case, but in general what you really need to talk about is the distance between all of those to all of those, and the spread of the distances also important. So in general, actually even defining what it means for this is like a belief state 1 and this is belief state G. Right? And you're trying to figure out how close is belief state 1 to belief state G. And I don't want to actually get into that. You can start thinking about it right now, but it's not an obvious way. There's no simple solution as to what's the right way to define the distance between this set to that set. Okay? And we'll talk about this next time. But one of the points, of course, is that you could sort of make progress by reducing the uncertainty in your own state, because once you know where you are, you might know which direction to go towards one of the reasonable goal states. Okay, here this is also a belief state, except as I said, it basically means if you ever reach either this state or this state, you're done. Okay, now that also actually makes it clear that suppose I have the following belief state, S1 dash, S2, S3 dash, S2 dash. Sorry, S1 dash, S3 and S2 dash. Those are my belief states. That's my current belief state. Okay, and I know that my goal state is S1 dash, S2 dash. Am I done? You have to understand that, right? Okay, how about this? My belief state is S1 dash. Am I done? Yes. Okay, so you need to be careful in defining termination condition. Okay, a particular belief state is a terminating state only if every state in that belief state is a goal state. Do you see what I'm saying? And otherwise it's not terminating state. The reason, of course, is that if I'm here and I think I'm done, I could potentially have been in S3, in which case I'm not in the goal state. So in a belief state, when I put 3 states in a belief state, it's a disjunction, not a conjunction. I mean, don't be confused by the same notation we use. Normally, you would have used a notation like this, P, Q, R as a state, but there you normally mean P and Q and R. Okay, when we write belief state description, S1 dash, S2, S3 and S2 dash, it's this or this or this. That's why it is uncertain. Okay, can you have conjunctive state uncertainty? Can you have conjunctive belief states? That means you are in, sorry. Can you, instead of saying, can I actually have a state like this, S1 and S2 and S3? Only if you're a Superman, basically, because you're saying the agent, you already said all these states are different states, and apparently you are simultaneously in all 3 states at the same time. You don't expect it to happen for the kind of rickety robots you buy. Only Superman can do it. So we don't talk about conjunction. That's why it's reasonable to just think, it's obvious that when I write S1 dash, S3, S2 dash, the only reasonable connective to put is disjunction. Conjunction wouldn't have made any sense. So I don't say it anymore. Okay. So that's actually something to remember, that the plan terminates if in fact current belief state is a goal state, and you say it's a goal state if in fact every state in the current belief state is a goal state. Okay. Now coming back here, so search is in the space of sets of states. So if you have do not have any distributional information, all I tell you is that you are in, you could be in a subset of the total number of states, total set of states, then obviously the number of belief states, the number of distinct belief states is 2 power s, right? If s is the number of states, then every subset is going to be a possible state for you. Okay. So the number of belief states is 2 power s.
Even the empty set?
Good point. Good point. You can get empty set during planning, but not otherwise. If the robot finds itself in an empty set, it could actually happen if, depending on the way you define actions. For example, if actions have preconditions. Okay. One very interesting question because of the fact that you are now thinking of S1, S2, S3, okay? Suppose I have an action A1 which is defined for S1, it's also defined for S2, but it's not defined for S3. It's not allowed, you cannot do action A1 in S3. Then what happens is you can't actually talk about what is the belief state. In fact, if you do, you can talk about it. In this case, the belief state that will come after you do A1 in this belief state is empty set.
So it's kind of like you have inconsistent beliefs.
Basically no, because more importantly, when you wind up doing A1 in S3, you are no longer, essentially it's undefined. Right? If in the normal logical, in the normal notion of preconditions is, if you do an action in a state where it's not allowed to be done, then the returning state is undefined. Okay. By the way, so in fact we talked about this in the very beginning of the class, and I said, in fact, this was this issue that if I try to lift this, with my single hand, and just because I don't have the ability to lift this, the world shouldn't come to an end just because my action failed, right? It should just leave the action, the world in the old state. Okay, and to be able to do that, normally you avoid having actions with preconditions. preconditions, having preconditions for actions makes the planner's life easy, but it's actually a bad thing from the point of view of modeling. Do you guys understand this? Right? If one way you can prove that the world will end is you try to do this action without its precondition being true. Whereas in my case, so which basically means in progression search, you would only consider actions whose preconditions are satisfied in the current state. That will reduce the branching factor. Whereas if every action can be done in every state, then even those actions whose preconditions are not satisfied have to be actually done, and they will just become a no-op action. Okay, so it's from a search point of view, it increases the search. So which is why people try to do these preconditions. But preconditions actually are a big mess in terms of modeling. They are a big mess in terms of modeling even for deterministic worlds. And they become even more of a big mess for belief states. Why? Because in the belief states, even if this action works in most of the states, but it just doesn't work in one of the states of the belief state, you can't do the action. Now, think about the following thing. Suppose the robot is starting with complete uncertainty about its state. Complete uncertainty about its state. That means it's in one of S1 to S million, which is all the total number of states. Suppose it has 25 actions. It's not too surprising, it's not too out of ordinary to believe that each of these 25 actions probably will have at least one state in which they won't be applicable. There are a million states, there are 25 actions. I would hope that at least each action would probably be not applicable in at least one of the states. Then what happened now? This guy can't do a thing because it has 25 actions, but it can't actually project any of them because each action would be doable in one of the states and the state is undefined. Because of which you would actually notice that by the time you come here, you tend to forget about preconditions. When you think in terms of belief space and actions, on the belief states, the need to avoid having preconditions, becomes even more. So it was there before, but it becomes even more now. So you normally assume actions are always applicable, and they will give you their effects when the quote-unquote preconditions are satisfied. Otherwise, they'll leave the state alone. Okay. So that's the short answer to your question. In fact, there are a large number of empties that can happen. For example, so this guy could do any one of these actions in this million-state robot. Can do any one of its actions. He'll get into empty because it no longer knows which state it is in. Okay. So now the other interesting thing is if I now tell you a little more about the uncertainty. Previously I told you that you just don't know which state you are in, but now I'm being kind of nicer to you and I'll tell you distribution information about your uncertainty. Now how many belief states are there? So this is useful to know that, for example, with non-deterministic uncertainty, if you were originally in a space of states S, you will now be in a space of belief states, which is 2 power s. Now, of course, in the back of your head, you know that if you originally have v variables, v Boolean variables, this would have been 2 power v, which is the number of states, and this then would have been 2 power v. Right. But that's the claim. That's the. So not having eyes isn't a good thing. Right? Because it looks at, you cannot distinguish between states of the world. Okay, so now the other interesting question is, if I give you a little more information about your uncertainty, not only do I tell you you are in this subset of states, but I tell you this is the exact probability that you are in this state versus this state versus this state. That would be a stochastic belief state. How many belief states are there when you have stochastic information? I gave you more information, so your life should be easier somehow, right? And yet, unfortunately, it becomes harder. Because essentially, the number of belief states are infinite now. Because you can take just the same non-deterministic belief state, S1, S2, S3, and you can write infinite number of distributions over S1, S2, S3. Just 3 positive numbers that add up to 1. That's a distribution. Okay, so in some sense, essentially you are able to, with stochastic uncertainty, you are able to split hairs. Okay, which is both a bug and a feature. It's a bug in the sense suddenly now you actually have a much larger space. Okay, it's a feature in the sense that with non-deterministic uncertainty, normally you can't do much. In some cases, you cannot do much more than saying, I am in the goal, that's it. Suppose I give you a plan, what kind of guarantees can I give you for that plan? Normally one guarantee you want is, I have reached the goal state. With these actions, after these actions, I have reached the goal state. Now we'll talk about what kind of actions can be done. Let's leave it at it right now. But so you do a bunch of actions, you will be in the goal state with 1.0 probability. That's for sure. If it's not 1.0, then basically in the case of non-deterministic uncertainty, it's all the same. It's either for sure or wishy-washy. Whereas in the stochastic case, you can talk about degrees of wishy-washiness, right? You can say this particular one reaches the goal with 0.9 probability. This one reaches 0.7, this one reaches 0.3, this one reaches 0.2. Whereas for the non-deterministic guy, the only guy who is a plan is the one who succeeds. Everything else is considered just useless. Do you see what I'm saying? So what that means is actually life is, again, this is one of these bad things to say, but it is true. If you do not have a bunch of, if basically in some sense all your lives would be much simpler if you have no hands to touch and no eyes to see and no legs to feel or whatever, and no ears to hear. Because in essence, nobody can tell you that you're being stupid by not solving this problem. Okay, the brain is completely out of the picture if there is nothing brain could have done to differentiate which state you are in, right? So there are fewer problems I would even be able to ask you. So in some sense your life is easy. Okay, the moment you start having eyes and and hearing, etc., then I can give you problems which other people having eyes and ears can solve, and since you couldn't solve, you get a C grade. You see what I'm saying, right? So it's like it's like a weird situation, but in some sense, the increase in the size of the space is both a feature and a bug. It's a feature because now we're able to actually talk about different kinds, a larger degree of ability to solve a problem. Okay? And then anyway, this is the part we won't come back to this. So here it is infinite number of states, and this is the part we won't come back to right now. We'll come back to it next week when we talk about POM-DBs. Yes, sir?
The distribution of the belief states be conditioned upon the action that you perform.
Distribution of the belief states be conditioned. No, well it is in the following sense. Basically, we'll talk about actions in a minute, but actions modify states. So when you do an action in a state, you get some new state. So the new belief state is a function of the old belief state and the action you did. So yes, it is. Okay? Okay, now, if you do have state uncertainty, how does it get resolved? How do you resolve the state uncertainty? How do you reduce the uncertainty that you have? Right? Now, of course, the worst possible case of state uncertainty is that you have no clue where you are in the entire world. So, S1 to Sn are all the possible states. And then, it's very unlikely that people will say, yeah, whatever you do, it's a goal state. It's not likely. So they might be very, very, they might be very, very nice people, and they'll say, well, if you are in states S500,000 to S million, then it's a goal state. You still, unfortunately, are no closer to solving it because you are from S1 to, you think you are anywhere between S1 to S million. Right? So how do you resolve the uncertainty? How do you reduce the state uncertainty? There are two ways. Okay? One, of course, actions can reduce uncertainty. Just actions. Okay, so you can do an action without knowing where I am and may have less uncertainty afterwards. right? I mean, so for example, there was a, I mean, again, so there are there's a children's poem that I used to read to my kid that, in the forest, different animals are sleeping or not sleeping. So you don't quite know whether they're sleeping or not sleeping. And at one point of time, the elephant snores, after which you know that everybody is awake. Okay? And if you are more politically inclined, we didn't know whether there were weapons of mass destruction before in Iraq. But after we just sort of flattened every little place, we know there aren't any. Right? It didn't matter whether they were there before or not. In the end, after we flattened the place, there aren't any left. Right? So, I mean, you might say, so basically doing actions can reduce uncertainty. And again, I don't quite know, I have blocks in different configurations. I want a clean slate. Zoop. All the blocks are down. Now I have a clean slate. Whenever several people actually do this, I mean, when they, instead of actually cleaning their offices, they just move from one office to another, leave one home and go to another home. Actions can reduce state uncertainty. Okay? Which is actually a very interesting thing, which basically means that even if, so that's one way of reducing the uncertainty, state uncertainty. The other one, which, yes sir, go ahead.
Is there a notion of a sensing action?
Yes, that's the next one. Because the other way is essentially by observing. Okay, so the way you actually reduce the uncertainty is by observation. Now you might say, what do you mean? You said it's not observable, that's why you got uncertainty of the state. The important point is that there are degrees of blindness. Okay? I have 20/20 vision, that means I can see everything that humans are supposed to be able to see, versus I am blind as a bat, which means I can't see a thing. And there are degrees in between. Right now I can see you, but if I have to read something, I can't see. Then I have to put my glasses on. Okay? And so, basically the interesting part, in some sense, the state uncertainty is because of partial observability. So the observability can also be at two extremes: fully observable, which is what we have done till now, fully unobservable, which basically means you have no sensors whatsoever. Only you can just affect the world. And one of the interesting things is, even if you just have effector actions, you can solve problems of certain kinds, because the effectors can reduce the uncertainty. Not necessarily in the desired way. Okay? But for example, if we had a goal about keep all the people in Iraq alive and still figure out whether or not there were weapons of mass destruction, you can't do, without sensing plan. By the way, a plan which does not sense is also called a conformant plan. Basically, it's only affecting actions. It has no sensing actions. Till now, all the plans you have seen are conformant plans, because you never talked about sensing actions till now. Once you have partial observability, you need to talk about a different breed of actions called observational actions. And a pure observational action essentially just tells you something about the current state you are in without changing that state. That's a pure observation. But then, you have Heisenberg, right? What did Heisenberg say? Right? Heisenberg said you can't actually observe a damn thing without changing it. And of course, he was talking about quantum uncertainty. And so it's like, can you find out whether dad is asleep or not? And you send the little kid in, and the little kid comes and says, "Dad, are you asleep?" Well, now I'm not. So that's not a particularly smart, observational action. It's not a pure observational action. Okay. So in general, interesting thing is that because of partial observability, now apart from the normal actions that you have loved until now, you also have pure observation actions. And you can have actually something which is in between, which is an action which has some effect and some observational, some knowledge effects and some actual world effects. We are full of those, right? I mean, it's like we get MRIs done to see whether or not we have brain cancer. You do too many of them, you will get brain cancer. Right? I mean, CAT scan, I think. CAT scan is the one that they do for the insane. Okay, so every possible medical test is supposed to be an observational test. It's supposed to tell you whether or not this guy is suffering from this particular disease, but they might cause other diseases, which this guy doesn't yet have. And so they are both causal and observational effects. Okay, and it becomes a much more interesting issue in actually modeling, actions which have both causal and observational effects. In the beginning, we'll actually mostly talk about two types of actions: purely causal actions and purely observational actions. Yes, sir.
I'm a little confused about the difference between the two. In my understanding, an action takes you from one belief state to another.
Yes, no, actually no. An action, so the interesting thing is that for a causal action, you don't change the definition of an action just because. So suppose I have a way of stacking one block on top of another block. That action doesn't depend upon whether I have eyes or don't have eyes. Its effects are the same whether I knew which state I was in and whether I happen to know which state I was in or didn't know which state I was in. So another way of thinking about it is, suppose I have an action A1, which, because we are talking about, and let's assume that just S1, S2, S3, S1, S2, S3, okay, and then, so I would say, if you do action A1 in S1, you would get to S2. If you do it in S2, you get to S3. If you do it in S3, you get to S1. Okay, and I'll assume that in every other place, for now, you can either say it's not defined, or you could say it just leaves you there. I'll assume it just leaves you there. Okay, and similarly, I have another action A2, which has S1, S2, S3. Remember, the reason I'm writing it this way is because I'm talking about atomic actions. I have taken a step back in terms of, we are no longer talking about preconditions and effects. We'll get to that in a minute again. Okay. So in this case, let's say if I do an action in S1, let's say it goes to S3. If I do in S2, it goes to S1. And if I do it S3, it goes to S2. Okay. Now, suppose I am in a belief state S1, S2. If I do action A1, the definition is that you may not know which state you are in, but the action knows which state you are in. Okay? So basically, if you happen to be in S1, remember that there is no fuzzy logic here. Either you are in S1 or in S2. You don't know it. But the universe knows which state you are actually in. When you do this action, if you happen to be in S1, then what do you get? S2. And if you happen to be in S2, you would get S3. So that's your belief state after doing this action.
So the belief state is not read as saying the agent believes he is in either S1 or S2. Is that the universe is saying he's in either S1 or S2?
No. This is what the agent believes, that it is either S1 or S2. After it does action A1, it can simulate what its belief state would be. Its belief state would be A1 being done in S1, union with A1 being done in S2.
Okay, so he performs the action, now he says, okay, I'm in either one of these two.
Yeah.
So if he does now a sensing action,
that's okay. No, all I'm saying is this is the new current belief state. This is BS0, this is BS1.
Okay, so that I understand. Suppose that A1 is a sensing action, however.
We didn't talk about sensing actions right now. Wait for that question in a minute. Okay. All I was talking about is the causal actions don't have to change.
Yeah.
Causal actions don't have to change. Okay. And one more interesting thing, as long as I have this picture, suppose I went ahead and decided that A2 is a non-deterministic action. If you do it in S2, you would get S1 and S2. What that basically means, it's either non-deterministically takes you either to S2 or to S1. I'm sorry, not this way. I think it should not be 1. Yeah, you could do it 1, 2, but I'll do it this way. S3. The moment I have more than 1, 1, that means it's a non-deterministic action. Right? So, if I do the action A2 in S2, I can be either in S1 or in S3. Okay? And everything else, if I'm in S1, I will still be in S3. If I'm in S3, I will still be in S2. Okay? Now, the interesting thing is, if I do the same action, S1, S2, followed by A2, right? Then my new belief state would be, when you do S1, when you do A2 in S1, A2 in S1, I get S3. When I do A2 in S2, I get S1 and S3. In this case, it turned out that you already have an S3 there, so it's still S1, S3. But in general, non-deterministic actions can increase the belief state's size, which is actually interesting. They can increase the belief state size, they can reduce the belief state size, they can leave the belief state size at the same level. Okay? That's the problem with causative actions. The belief state size can keep reduced, non-monotonically changing. Okay? Now, the other type of actions are observational actions. Now, what is a pure observation action? A pure observation action essentially gives, so I can take this out. So a pure observation action essentially gives to be an observation. And so basically if I do this action AO, it would give me some observation about the underlying state I am in. Okay? So there are state literals S1 etc. up to Sn, and there are observation literals O1 etc. up to Om. Okay? When you do an observation, it will give you, these literals. Now the interesting thing is that there is some mapping between, basically you have this probability that S1, probability that you would get OI as the observation literal if you happen to be in state Sj. Okay? Now this is basically given to you upfront. So what states will give what kinds of observations is given to you upfront. Now based on this observation, then you can invert it and get information about what states you are in. Now, since I said this is a probability, but I said I'm actually right now going to talk about non-deterministic. So this is the model that you will use in POMDPs. Given the state, what is the probability of this observation coming? But in the case of non-deterministic uncertainty, we assume that the observation model is such that these probabilities are either 1 or 0. If it's 1 or 0, it's deterministic logic. Do you see what I'm saying? So a state will give this observation or will not give this observation. No in between. So either the probability is 1 or probability is 0. Given this, when I get the observation literals, I can then essentially filter my states through the observations to see which states I'm really in. Do you understand what I'm saying? Okay? That is the filtering problem. This is a problem that you did not have before. Why? Because you always knew which state you are in. You just had to open your eyes and you knew which state you were in. Okay? But when you have uncertainty about the state you are in, and if there are partial observations, okay, then you will essentially be able to filter your state uncertainty. Now, can you tell me a model, a version of this model, which will essentially be equal to having full observability. What would be the version of this model which will be equal to partial observability? I'm sorry, zero observability. Yes?
Single observation.
Single observation. That's one way. So every state gives the same observation. You're still alive. Well, actually, alive is not good because there could be states where the agent is dead. But basically, every state gives that observation. So the IDF of that state, IDF of that observation is basically 0. Okay? In fact, so I do these two pieces of work in my world, databases and AI, and only I think they are connected. Nobody else does, and right now I'm thinking they're definitely connected because it's all about IDF of the observations. Okay? If the IDF is 0, then it's basically an unobservable world. So that means what? When will it become fully observable? IDF has to be maximum. When is IDF maximum? If an observation is given only by one state, every state gives its own unique observation. In that case, essentially you might as well say the observations, there is a one-to-one correspondence between OI and SI. In which case, essentially, you know which state you are in. The in-between cases are the interesting cases. So in some sense, this also makes you realize that what observations do is to build equivalence classes over the state space. Okay? And if you have no if observations have 0 IDF, that means you're getting the same observation from every state, then essentially your state space is partitioned into one partition which contains all the states. So doing observation doesn't give you any information. If your observation actions are such that the state space can be partitioned exactly into S partitions, with each partition having one state, that's fully observable. The in-between basically means here are a set of states, I don't quite know which of them I am in. Given just my observations, I would never be able to tell anymore which of these states I am in. And then here is another subset of states, and I would not know which of them I will be in, given just the observations. Yes, sir?
Do the observations correspond to sets of state variables?
Observations, when we get to the factored model, we will make the connection between observations and the state variables, which would be the reasonable thing to do. Okay, one of the interesting things, since you brought it up, again, since we can't forget about the fact that we have seen better life than atomic models, we could actually talk about the fact that if you in fact are considering, and this will come back again, I guess, either sometime today or tomorrow or Wednesday, if you have P1 to Pn are the propositions making up the states. Okay? And you can think of an observational action to be giving you an observational action in general gives you true phi. For an arbitrary logical formula phi, it will tell you whether it is true in your state. That's what a most general observation action is. Okay? A special case of observational action is where phi is a state variable. It's a single state variable. That's simple. So basically, you happen to have observations that corresponds to individual state variables. This is not obvious, by the way. I mean, there is no reason why your observational actions will correspond to the actual state variables of the world. In general, all you can expect is an observation would be true if some complex formula over the state variables is true and false otherwise. Okay, but if it is about single state variables, which is a special case of sensing actions where you happen to know exactly which where your observational actions is always over a single state variable. Then the question is, how many variables are covered? If you have an observation action for every one of the state variables, then it's a fully observable world, because it will split it exactly into a partition of S states, where S is 2 power P, 2 power N radians. Okay? If you happen to only be able to figure out, you only have observations to figure out whether you are on P3 or P7 or P12, okay, and you have a total of P10, I'm sorry, P20, right? Then you had 2 power 20 states, but you can only split it into subsets, actually 6 subsets, right? Based on 6 subsets based on this is P3 true, this is P3 false, this is P7 true, this is P7 false, this is P12 true, this is P12 false. That's all you will be able to tell. Okay? Yes, sir.
Earlier you mentioned the idea of trying to minimize the search space, the state space, using these observation actions.
Mm-hmm.
Which state space? The one of the...
No, I'm not minimizing the state space. I am reducing the state uncertainty for the agent. So the number of states are still 2 power n. But a given an observation action, an agent can tell. So suppose if the agent currently thinks that it's in S1, S2, S3, okay, it's one of the 2 power n states, and it doesn't quite know which of them it is in. Okay, by doing observational actions, it can figure out. Now the tricky point about observational actions, a very interesting point about observational actions, is how do they work during planning versus during execution. Okay, so here is my thing. So I have to, so I'm starting tomorrow to go off to LA for a whole day, and I'll come back in the evening. And let's say I wake up in the morning, and for whatever reason I have uncertainty in my state. I'm not quite sure whether my laptop is fully charged or not. Either it's fully charged or it's not fully charged. Okay. Let me see what. Yeah, so I could, and I know I want, for whatever reason, I want my laptop to be charged by the time, I go to the workshop. When I'm in the workshop, I want the laptop to charge. Okay, so I could do the following thing. So I could say, since I have the uncertainty in the state, I can put the following thing. When I get to the workshop, I'll see if the laptop is actually charged. Because right now I'm running, to catch my very early morning flight. I don't even want to open my ancient laptop and let it come up, only to say that it has no battery left. Okay, so I'll just say, when I go to the workshop, I'll check if the battery has charge or not. That's my answer, that's my sensing action. Now, when I put this sensing action into my plan, I have now opened the possibility that when I check, it will say yes it is charged or no it's not charged. Yes it is charged, I'm done. No it is charged, I better have a plan for that too. So then I hope that, hope springs eternal, right? So you would say, when there is no, battery charge left, I'll open it when I get there. This is my plan. I'm running right now. I don't know whether my battery is charged or not. And I'll just decide not to actually figure out right now. I'll just put a sensing action, which when I get to the workshop, I'll check whether the battery is charged or not. If it is charged, I'll continue working. If it's not charged, I'll find a plug point and plug it in. That's part of my plan now. Now this plan is called a contingency plan. When you do sensing, you get multiple contingencies because you can't will the sensing action to come one particular way. Do you see what I'm saying? So, because if you can will sensing action to come one particular way, that means there was no uncertainty in the state to begin with. right? So when you put the sensing action, you have to allow the possibility that since at the planning time, you don't yet know what happens to the sensing, what the outcome would be. So you have to provide what to do if you are in this side versus this side. Which essentially means that if you are doing sensing actions, you need to do contingency planning. Okay, just a second. Okay? It's no longer a straight line plan. You can of course assume to not consider some contingencies, right? Then you have to ask yourself, why do you even want to sense? Right? For example, if I said, I'll assume, I'll check whether the battery is charged or not, and I'll be charged and I'll start working. Then I might as well avoid wasting my time of putting the sensing action into my plan, because I don't really care what it says. Do you see what I'm saying? If you really care about what the sensing action could say, since it can say either this or this, you need to, plan for both contingencies. If in fact it was a kind of a case where the observational, if it was in fact the case that the sensing, when you sense, there's a higher probability that one outcome will come and lesser probability another outcome will come, then I could have done limited contingency planning. That means I only consider some of the contingencies and leave the others. Now, of course, one other issue is that if I decided to actually look at the, I'll assume that the battery will be charged. If not, I'll figure out what to do then. That basically means I am leaving the plan to fail, and if it does fail, I will replan, starting from there to get to the goal state. That would be, so when you have this kind of state uncertainty and you're throwing in observational actions, you can either do full planning upfront to make a complete tree plan. So start from the top, where you are in a belief state. Whenever you do an observation, the belief state sort of gets split into the part of the belief state that is consistent with the observation. So the belief state, so an action can say, I will tell you whether O1 is holding or not. Okay, then on this side, if it says O1 is holding, then you get a belief state where all the states correspond to giving O1 with probability 1. Okay, and the rest are the original belief state minus this set will be the other subset, other belief state. Okay, and I could decide to plan for these, both the belief states up front, or I could decide to interleave planning and execution. So keep planning up until the point where sensing is needed, and then stop doing planning. Go do that sensing, figure out what the sensing says, and start doing planning for the actual world you currently are in. Which one is a better idea? Should you be doing full contingency planning? Should you do limited contingency planning? Should you do sensing, interleave sensing and planning? Which one is the right way to do? Depends on the cost structure of the domain. Okay, and so to the extent, if in fact the sensing tells you other way around and you have a good probability of doing replanning and getting back, then you leave that contingency unplugged. Okay, so for example, when I'm going to LA tomorrow, then I also probably did not get breakfast, then I'll say I want a specific kind of breakfast, let's say only a subset of things, maybe I'm a vegetarian, I want to eat some vegetarian breakfast, and I could decide to make a full contingency plan. What happens the first, because again I told you I'm going very early in the morning, what happens if the first store is closed, what happens when the second store is closed, what happens when the third store is closed? To say to heck with it, in the US airport something will be open. Okay, and then I'll go there and then check and what is available and then find something to eat. There I have decided not to plan upfront. Okay, but I won't do that for actually finding a flight. I'll just go to the airport and figure out if there's a flight, and then if so, I'll take it. That's not a good idea. LA, it might be a good idea, definitely not a good idea to India, because there are very few flights going from Phoenix to India. Okay, so it's a question of the plan failure and the probability that you can do replanning that decide whether it's worth doing full contingency planning up front, limited contingency planning, or just combined sensing and planning, interleave planning and execution. Yes?
The way you describe the sensing action for your example, you said if I look at the laptop, it might tell me that it's powered on, it might tell me there's no power.
Mm-hmm.
How is that different from just a regular non-deterministic action?
Because a
It
non-deterministic...
might take you to state S1, it might take you to state S2, you don't know.
No, that is... So the point is that the underlying state the world is in has not changed. It's my belief that has changed.
So one kind of describes the transition between belief states, the other one describes transitions
In your knowledge
between
state.
those.
In your yeah, exactly. It's telling you about your own knowledge state. Your knowledge state becomes more refined when you do sensing. You can also make it more refined by just doing actions, as I pointed out. You can do state uncertainty. You can reduce state uncertainty in either way. You can use these actions both to get closer to the goal and to reduce the uncertainty in your current state. These you mostly use only to reduce the uncertainty. Okay, they don't make you go closer to the goal. Because whatever states you are in, you are still in. It's just that it tells you which of them you currently really are possibly in. Okay? Okay, so now the two interesting problems, I already talked to you about this, that's this side. Two interesting problems that the state uncertainty has brought in is the state estimation problem, which is a pretty interesting problem for somebody who doesn't know where they are. Okay, in particular, using sensing and action outcomes to figure out what state the agent currently is in, that's state estimation. What state will it get to if it doesn't do anything further now onwards, that's prediction. And then finally, what state did I start from now that I seem to be in this state? Did you understand what I'm saying? Sometimes if you woke up in the morning, you didn't quite know whether or not you had put on your the same colored socks on both legs. And then you came off here, and then all your friends are looking at your feet and laughing. Now, there are multiple possibilities. One, of course, is that they're laughing because of your socks. If that is the case, then you know actually whether or not you had the same color socks when you started. So the observation now tells you more about your state before. That's called the smoothing problem. Okay, so using the observations of the later states, improving your estimation of the former states. That's the smoothing problem. Now all these problems become much more interesting in general for stochastic uncertainty, and somewhat less interesting for for non-deterministic uncertainty. Okay, and then in terms of the planning problem, so this itself never even existed before, but much of what most robots do is figuring out where the hell they are. A robot spends its lifetime figuring out where it is, unless it has a buried cable or something which allows it to figure out exactly where it is. Okay, so if I go back to, let's see, where is this? This one. Okay, so what's happening there? That's a robot essentially localizing itself from the sonar information. Okay, and so in the beginning there were red dots all over the place. That means its belief state essentially said it could be in any of these places with these different probabilities. As it is doing actions and getting new observations, it progressively reduces its state uncertainty. Okay, and in this particular case, the robot actually knew the map of the world. It knew the map, and it just did not know where in the map it was. Okay, and what is being done here is a classic filtering. Do an action, recompute my state, belief state. Do another action, recompute my belief state. Do another action, recompute my belief state. And that basically reduces, because of the observations you get after the actions, you can reduce the uncertainty as to where you are significantly. And when you happen to know after doing these many actions that you are here, you also will know that I started from here. Because I hope that you have the brain to remember the actions you did. Right? And if you do, then you will know where you started from, because you know where you are right now. Okay, it's a very nice, and you know, if the variation on this is, of course, not even having a map. And that would be simultaneous localization and mapping, you know, and there are techniques for that for robots, SLAM, you know, simultaneous localization and mapping. Okay, these basically are problems that we did not even consider before, because there is no point in talking about those problems unless you have state uncertainty. Okay, and then in terms of planning with these, you can do planning without any sensing. Just because you have sensing actions doesn't mean you have to use them, right? I could say, for example, what is the maximum I can do without doing any sensing whatsoever? Okay, some problems can be solved, some cannot be solved. Because remember that actions can reduce uncertainty sometimes. Bomb in the toilet problem, which I mentioned to you guys, right? Did I mention bomb in the toilet problem? So bomb in the toilet problem is this problem where there are two identical packages in a bathroom, one of which has a bomb. It's going to go off any minute now. You are in the bathroom. You can't get out of the bathroom, right? And you need to, you know, defuse the bomb so that you will live. And there's only one action. Because you're in the bathroom, what can you do? Dunk the bomb and flush it. Okay? And so if you flush a package, it becomes wet and bomb doesn't work. Let's hope that. Okay? Now the question is, you will never know which these packages are identical. If you try to open them, they'll go off. Okay? Can you survive? Yeah, you can. Well, just, you know, let's assume that you have a really big toilet, and so you can put multiple packages and dunk it. Do you see what I'm saying? And there was a case where without sensing, you were able to survive. Okay? And so so basically, in that case, you know, you have confinement planning. Now, suppose it turns out that you are in the same toilet. Now, this is one of these, you know, low flush toilets, and it will only be able to you'll only be able to flush one of the packages. After that, it gets stuck. Now, can you survive?
Mail them to the EPA.
That's true, but you know, right? Now you can't survive. Now, basically, unless you sense and figure out which package has the bomb, you can't survive. Now, the guy who could have sensed can survive in both cases. The guy who can't sense will only survive in some cases, not the other cases. Which is why don't feel, you know, I mean, if you ever feel being too jealous of people who are missing eyes and, you know, and hearing, etc., don't. Okay, it's true that it looks as if, I mean, there's this great Seinfeld episode where George, does any of you know Seinfeld? So George basically gets onto this wheelchair because he feels the wheelchair people get really good deals. And, right? So anyway, the point, of course, is wheelchair people may get some really good deals because we have sort of civilized ourselves to kind of help people who are disabled. But it's also the case that there are bunches of things that they can't do. Right? And so essentially, if you don't sense, I mean, and if you don't have, in this particular case, if you don't have the sensing ability, in that case actually it's the affecting that's missing, in the wheelchair case. But in this case, if you don't have the sensing ability, you may solve some of the problems, but not others. And if you also commit to use sensing, then you basically are doing full contingency planning, or limited contingency planning, or interleaving sensing and execution. Okay, those are the problems that you can't get to because of partial observability. Okay, so that's all basically I have to say. I mean, I expected to show the rest of the slides, but I just showed one slide and explained, I think, what I wanted to say about the atomic model. So here they're talking about the state model. They're talking about the cardinality of the belief state changing when you do actions. Sometimes it goes up, sometimes it goes down. And here is, for example, a conformant belief state search, where essentially in the space of belief states, an action takes a unique belief state to another unique belief state. So interestingly enough, and it doesn't matter, as I showed you based on those pictures there, it doesn't matter whether the action is deterministic or non-deterministic. You'll always go from a single belief state to another single belief state. Okay, so in some sense, you can take uncertainty in state and compile it away by searching in the space of belief states. Not surprisingly, that's what we'll wind up doing in the case of POM-DPs too. You have uncertainty in the state which makes it a non-MDP. It's not a Markovian decision process anymore. But you can make it Markovian by thinking in terms of belief states rather than the individual states. And they will become Markovian again, and then you can just do fully observable MDP. Okay, so the other interesting question here is that when you're going from one belief state to another belief state, by the way, notice that in this case you have, this one is actually about vacuum agent, and you can go back and look at this. So once you do this action, then you do the same action on all the belief states, all the constituents of the belief states, and figure out what new states can happen, and then put a big circle around them. Those are all the states that can happen. Okay, just a second. And here is the full state space for the conformant, planning for this a vacuum cleaner, which basically starts with 2 rooms, and the vacuum cleaner is in one of the rooms. There may or may not be dirt in both rooms. And the final goal state is to be, presumably, I believe which one, I think these two are the goal states. Final goal state is to be in one of the rooms and both rooms are clean. You can even say, if you are one of those really kind of compulsive people, you would say that if the vacuum should be put away in the right-hand room. So then you are harder to please because this is the only goal state for you. Okay? And the question, of course, then is how are you going from any of the states to one of these states? And they will be just paths. This is not a hypergraph. This is a normal graph. Okay? Except the vertices correspond to sets of states rather than single states. And notice that not all sets of states are present in this graph. Because which sets will be present depends on what actions are actually possible. Okay? And then basically, since in this particular case, I think this is 1, 2, 3. So there are 3 state variables. So there should be 8 states total. Maybe there are 8 states. 1, 2, 3, 4, 5, 6, 7. There should be 8 states here, right? Yeah, there should be 8 states, and there seem to be more than.
Some are.
There is a problem here for some reason.
There's 8 states.
There's 8 states in the
biggest belief space.
There should be 8 belief states total. Oh no, I'm sorry. You're right. Okay, I'm sorry. You're right. There are 8 states in the real world. So which means there are 2 power 8 belief states. So which means there are 256 belief states, but in the reachable graph there are only much fewer than 2 power 56. 256 belief states, which is the point I was trying to make before I kind of blanked out. Okay.